Now the rest of the stuff on that board is kind of a mess, so I'm going to just do this right in front of your very eyes. Okay, so we want to show, or at least get some idea of why the determinant of AB should be equal to the determinant of A times the determinant of B. First of all, assume determinant of A is not 0, the determinant of B is not 0. Then A is a product of elementary matrices. And if E1, E2, etc., up to E sub P, where P is the number of elementary matrices we need, are used to reduce A to the identity, which can be done as long as the determinant of A is non-zero, then A is going to be E1 inverse, E2 inverse, E3 inverse, up to E sub P inverse, for some set of elementary matrices. And let's let B equal F1 inverse, F2 inverse, up through FQ inverse. There are Q matrices used to reduce B to the identity, elementary matrices, and these are the inverses of those matrices. And if they're multiplied in this order, this will be the matrix A, this will represent the matrix B. Okay, well, the determinant of a product of elementary matrices is the product of their determinants. And I'm going to give an argument for that. I'm not going to give a completely rigorous argument, and I'm going to suggest that maybe you patch it up and make it completely rigorous by, for example, addressing what if determinant of A is 0? Does that necessarily mean the determinant of AB has to be 0? Okay. Well, anyhow. Okay, if you have a sequence of elementary matrices, well, there are three kinds of elementary matrices. If E sub I switches rows, the determinant of E sub I is -1. We've seen this already. If we add a multiple of one row to the other, the determinant of E sub I is 1. And if E sub I multiplies a row by a number, let's call that number C, then the determinant of E sub I is C. And this is easily proven. Take any identity matrix and switch 2 rows, find the determinant of the resulting matrix, it's going to be -1. Adding multiples of one row to another, just add any multiple of the identity matrix, any multiple of any row of the identity matrix to another, the determinant is not going to change. And if you multiply a row by C in an elementary matrix, meaning if you multiply a row of the identity matrix by C to get the elementary matrix corresponding to multiplying that row by C, the determinant of that matrix is going to become C. Okay, it's very easy to prove by looking at what these matrices do, or what these operations do to the identity matrix. And of course, you perform the operation on the identity matrix to get the elementary matrix. So we can also kind of fill in here. In this case, EI inverse equals E. The determinant of EI inverse equals the determinant of E. If you add a multiple of one row to another, determinant of VI is 0. EI inverse adds the opposite multiple of that same row to the other, and that undoes the operation. So the determinant of the inverse matrix is 1. The thing it undoes multiplying a row by C is to multiply it by negative C. So the determinant in this case of EI inverse would be 1 over C. Okay. Now, if the matrix does reduce to the identity, then we can express A as we say, we can express B as we say. Now, let's say okay, this means that whatever EP represents, whatever E1 represents, that represents the first operation in reducing the matrix A to the identity. And the matrix E2 is the second operation, matrix E3 is the third operation, and so forth. Okay, so some of these matrices will be could be row switches, not necessarily, but could be switches of rows. If we compare, well, in reducing the matrix, if you switch two rows, the value of the matrix, the determinant of the matrix, becomes negative. It's the negative of whatever matrix you did the operation on. So every time you switch rows, you've changed the determinant of your matrix by a factor of -1. You've multiplied it by a negative. If you add a multiple of a row to another, you're down at this stage, you add a multiple of some row to some other, you haven't changed the determinant. If you multiply a row by C, then you have changed the determinant. You've multiplied the determinant by C. Okay? So the list of things that these inverse elementary matrices do is the same as, and I'm kind of skipping a step here, which is why I'm hesitating. It's the same as what you would do to build the identity matrix with its determinant of 1 back up to the original matrix. Which means that the determinant of every one of these being the thing that you would multiply by the matrix, but by the determinant of the existing matrix to get the next one. If you multiply all these determinants together, you're going to get the determinant of A. Now, I'm not satisfied with the way I just said that. I need to illustrate it a little better, so I'm going to do that.